Okay, for people who are joining this live stream, we are going to do a working session about some issues in our physics project. And it's going to be me and Jonathan and Ed Pegg and maybe other people. The topic I want to talk about today was getting intuition about quantum mechanics through other uses of multi-way systems, particularly in things like games. So let's take a look here at what we're talking about. There we go. Let me, actually, I'll do that. Okay, let's recall what we were talking about previously. So the idea is that we have something like Tic-Tac-Toe. Let's take a look at, this is a minimal version of Tic-Tac-Toe here, in which we have a 2x2 board, and as soon as anybody gets 2 in a row, they win. So this is a multi-way system because we are, at every move, there are multiple things that can be done, and there are a small number of winning configurations. Okay, so the question is, what's the analogy between this and the multi-way systems that we've looked at in quantum mechanics? And how can we think about what's going on here? And in particular, is there a way to think about quantum amplitudes as a way of analyzing this game? And to what extent is the winning of the game like quantum measurement? And we made some notes previously, talking about, okay, blind chess, all right. Talking about the kind of, I'd already forgotten a bunch of the things we did here. This was a little while ago. We're interested in, okay, so I think the thing we would particularly like to do is to try and take a look at how to think about whether there is a specific way to formulate what we're doing in terms of games as in terms of quantum amplitudes. In other words, can you apply, so what we're doing is we're basically, this is a story of essentially blind tic-tac-toe, if I'm making sense. Yeah, Jonathan, Ted, others?
Yes, that makes sense, because if you make a move and the referee disallows it, then you'll know that your opponent has a piece on that space.
Right. But oh, I see what you're saying. I see what you're saying. Okay, but what I'm asking is, if we think about, so in the case of this tic-tac-toe thing, okay, so let's use our tic-tac-toe code from before. Okay, so let's remember what we were doing here. So we're looking at, okay, so my question is, in the quantum analog of this, what we're saying is every one of these essentially quantum states can be assigned a certain amplitude. And then we're looking at a superposition of these states. That is, we know only certain things as being some combination of these states weighted with certain amplitudes. Jonathan, does that make sense to you?
Yeah.
I think that we need to define what happens if I move on your space. There's 3 things that could happen.
Yeah.
My move could cancel out your move. It could just be told it's disallowed and I get to make another move, or I lose my turn.
Well, fair enough. But look, the thing I'm trying to understand is, if we were going to write this, okay, let's say we have a little piece here, we're going to write, does it make any sense to say that this game has gotten into a state that is like a a quantum amplitude where we're saying, it's imagine each one of these things. So let's say, if we have a, okay, so let's take this example. Let's say, I don't know, tuples, let's say 0, 1, 2, 4 partition. Okay, all right. So imagine we've got does it make any sense to imagine a little quantum state that is a combination, whatever it is, a bra, this thing, times some quantum amplitude plus some other thing with a quantum amplitude, etc. Does that make sense? Can we make sense of something like this? And then how do we think about, in the final state when we get to a win? So Jonathan, do you have any thoughts about, we're laying this stuff out in this branch shield space. That is, we are defining distances between. Let's take the next level. Well, in this particular case, we could just go. I guess we could just go another level here, right? And this thing, whatever that is, there we go. Right, we've got something like this, and we're asking the question, there is a notion of branch hill space here. So my question is, we talked about previously that there's some kind of score distance between states. Maybe. I'm not sure what that really means, but if we say here, if we imagine that there is a, forget that, and just say branch hill graph here. Okay, so in what sense can we think of, what is the analog of our entanglement distance for the game? So what happened here? This is a one move different thing, right? That's what it means to say the distance in branch hill space is one move was made differently. Is that right?
Right. Or that there was a common decision point at which there was a bifurcation. So yeah, obviously the natural metric is going to be related in a fairly direct sense to the score, or at least to the distance from winning of a particular player.
But isn't it the case that one unit in branch hill space is always, what is it? It's one unit in branch hill space is one decision was made differently, right? One unit in branch hill space equals one move was made differently. Is that right? Yes?
Right.
Okay, so now the question is, can we think about, the thing I keep on coming back to is we're trying to coordinatize branch hill space. Well, we're trying to say, alternatively, we're trying to describe, okay, so another question would be, our concept of geodesics in multi-way space, what do those correspond to here? I think any of those is just a sequence of moves. Any path here is a sequence of moves, right?
Well, yeah. I mean, with any multi-way system, if you trace a path through the multi-way evolution graph, it collapses to its classical analog. Yeah,
I understand. But what we're saying here is, okay, so we've got this, and this is our, whoops, what on earth happened there? Okay, this is our multi-way graph, right? And now we're saying, in here, any game is a path, and they're all geodesic paths. Right? They're all of the same length.
Right.
So all specific games are paths which are geodesic paths in this graph, right? Okay, so now the question is, when we think about a particular game, is it, and we might think about a combination of games. What is the analog? What's the analog of quantum interference? What's the analog? We're thinking about these different positions in game space, so to speak, corresponding to different amplitudes somehow. And can we understand what the analog of basically interference is? Do you see what I'm asking?
Yeah, but isn't that just, that's just resolution, isn't it?
What do you mean?
As in, the game has to resolve into a winning state at some, it's like an ordinary, the only thing that what we're doing here, the only sense in which what we're doing here differs from standard quantum tic-tac-toe is that we don't have an explicit measurement rule.
What is standard quantum tic-tac-toe? Is there a standard quantum tic-tac-toe?
Yeah. Yes, in ordinary quantum game theory. But obviously, the main difference with standard quantum tic-tac-toe is that you have, whenever you produce cyclic entanglements of grid squares, the player whose turn it isn't has the opportunity to choose how they make a measurement.
So I do not know about quantum tic-tac-toe. I guess I should have studied this. What happens in all right, I have an article here about quantum tic-tac-toe, but what?
The basic, obviously quantum game theory is just about taking ordinary classical game theory and saying, what happens if you could take superpositions of strategies or superpositions of initial states or entanglements of initial states? Okay. And then quantum tic-tac-toe is the natural extension to that. The natural specialization of that to the game tic-tac-toe. So you can have, so in particular, basically what happens is you relax the rule that you can only have one marking in a square at any given time. So you end up naturally with superpositions.
Okay. Of game states. So we're representing that in a different way here by saying that our superposition, we're not saying, we're okay.
But the point, that's my whole point, right? When you project, when you're discussing amplitudes, you're talking about how do we take some extended object in branchial space and project it onto a single space, right?
I'm not sure I am, but yes, you could. What I was imagining was this, which is, you're saying that the way I should think about this is by amplitudes for the different elements here, or what? Right.
So in that case, well,
it's not a very good case there. Let's pick a better
not normalized, case. But basically what you're saying is that the top right-hand corner is in some superposition of purple and orange, right? So there's a purple mark and an orange mark in that square, and they have equal weight in that particular case, assuming that the state weights are the same for both.
Well, but is it right to look at it this way, or is it better to think about it as a complete state here? Is it better to break the thing down into the individual squares, or it's better to think of the whole thing as a state?
In the separable case, it doesn't matter. They're the same.
Okay. But boy, people have, okay, I didn't realize this is one of these, this is, have people been there before questions is always interesting. And I have to say, it's sort of amusing to me that the stuff I found yesterday, actually, Don Knuth pointed out to me that the stuff I was doing, some stuff I was doing had been seen before 400 years ago, which is kind of a cool, we'll tweet this soon, but this is the chap who did it 400 years ago didn't get it quite right. But anyway, we'll see whether the people who did this, who looked at, okay, in any case. All right, where were we? We were thinking about, so you were going to explain something about, so I wasn't understanding this. Could you go back through it again?
What is this?
Well, this idea of okay, so this notion of quantum tic-tac-toe is saying for every individual square in the game that you can have a superposition for those squares. Is that right?
Yeah, in the sense that you can have a superposition of marks within each square. Yes.
Right, but what I'm saying is Right, Richard on live stream is pointing out to achieve entirely classical marks is a win in quantum tic-tac-toe.
Well, to achieve a winning configuration consisting of classical marks. So if you achieve 3 in a row entirely of classical marks, right? That's the whole point I was making, right? That the distinction between ordinary quantum game theory and what we're doing here is that in quantum game theory, it's conventional to define a strategy for measurement. So you would say, like I say, in quantum tic-tac-toe, as I recall, the way it works is you say, when you get a cyclic entanglement, then the player whose turn it isn't gets to choose how that thing is measured. And so then they end up collapsing the thing down to it. They end up collapsing a square containing a superposition of marks down to a square containing a single classical mark. And then, as we say, that the first player to achieve three in a row of classical marks wins the game. What we're doing in this is we don't have an explicit measurement strategy defined, and the measurement strategies we do define right now act on the entire state rather than on individual squares.
Okay, but so then you're saying in ordinary quantum TTT, one is doing operations separately, doing operations including measurement separately on every square. Is that right?
Right.
Okay, and so you can independently collapse. Okay, so let's just try to understand our case. So in our case, this idea of what is the idea in the case we're looking at when we think about a win? How do I have a picture with a win? There's a picture with a win. Okay. Oh, following is wrong. Great. Okay, maybe this is right. Okay, so this claims to be the case with a win for us. What is going on with this? You know what? This is a bug that needs to get reported. I'm running 12.2, and this here is a bug, and this is that outer that outer thing is wrong.
Yeah, I got it.
Take a screen capture of that, please.
Done.
Okay. Can you also make sure to copy me on the mail you send about that, please?
Yep. Will do.
Okay. Okay, so in this case, what can we say about the sort of traditional winning and how that relates to measurement? Because what you're describing previously is you're just saying every individual square has a quantum superposition in it, and measurement is just operating the way quantum measurement always operates. But the interesting case for us is to understand it, in this different setting. So what's the analog in this? In a sense, this is a completion, one of your favorite completions, Jonathan, of making an equivalence class of all states that have 2 oranges in a row, right?
Well, except it's not, right? Because the system you end up with is not still has one irreducible bifurcation in it.
What do you mean? Oh yeah, but wait a second. So there are 2 measurement results, is what I would interpret this to mean.
But you haven't performed. How does that? Okay, if that were true, how would a situation in which you have 2 measurement results differ from a situation in which you just have a superposition of 2 different things, 2 different eigenstates?
I'm not sure. I mean, I think that look, what is measurement in any of these interpretations? Measurement is you get to a situation where all the things that were previously quantum distinguished are now equivalent. Right? That's kind of what it means. What's that?
Right, exactly, which obviously isn't this case because there's still one big one missing.
What do you mean?
Because you have a superposition of orange and purple winning. So in the absence of a rule that specifies which of the two to select, this isn't well, it's not a measurement in that sense of the word measurement. You may be proposing a new sense of the word measurement, in which case I don't.
Well, no, but wait a minute. In all cases, right, you make a measurement and you can get different results from the measurement. Otherwise, it isn't a very interesting measurement.
You can get different results if you're in a different reference frame. Yeah.
Okay, so your claim, let's see if we understand this. Your claim is that given a quantum system, that in a given quantum observation frame, there is a particular sort of generational state that you can assemble.
If you pick a quantum observation frame, then at least the version of measurement that I thought we were dealing with is deterministic. The apparent non-determinism arises from the fact that the details of the quantum observation frame are not themselves observationally accessible.
Okay.
Right.
So let's think about that for a second. So what we're saying then in this case is, so maybe a better way to think about this is in terms of quantum observation frames. So in other words, what we could do here, forget winning and losing here, right? Just go all the way and now try and make an observation frame in which, see, I'm still trying to understand how this works, by the way.
It's exactly how it works in the ordinary formulation, right? That, the reason why tic-tac-toe is useful as an example, as I'm sure you're aware, is because every state is because everything is purely branch-like separated, because you can't have, it's purely space-like separated, because you can't have, classically, you can't have two counters in the same square. The win states are necessarily generational states, and only the win states are generational states. Or
what do you mean only the win states are generational? Why are only the win states generational states?
Or I guess win and draw states are generational states.
Why do you say that?
Because that's what a generational state is.
In other words, it's a state. I see. Your point is
in a 2x2 grid.
I understand. The win states are generational states because something has happened at every element. Right. So that's what you're saying. Is that a generational state is one where the rule has been applied. And okay, so I agree with this point that the
it's just like the conventional formulation that we have two possible generational states. You construct a quantum observation frame that preferentially selects one.
Okay, hold on. So what we're saying here is that first point, which is a good point, which is sort of obvious, is that there are no branch-like separated configurations because every square is spatially distinct, basically. Okay, so now what you're saying is, in this picture, if I wanted to distinguish winning and losing, I could do that by putting in a different foliation of this picture. If I wanted to distinguish orange wins from purple wins, right? I can do that by adding.
That's the definition of a multi-way game, isn't it? I mean, basically, if you have a two-player multi-way game, what you're saying is you have a multi-way system with an equivalence relation that's defined on it that collapses everything down to 2 or possibly 3 generational states, right? Player 1 wins, player 2 wins, draw, depending on the game.
Well, you're saying in the end, there's a completion. These are generational states right here, but you're saying you do a completion to make equivalence classes of generational states that correspond to the competitive outcomes of the game, so to speak.
Right, but that doesn't guarantee causal invariance, or else if it did, it wouldn't be a game because there would be a predetermined outcome. So then the measurement is the thing that determines who actually wins. like I say, in some sense, the formal definition of what it means to be a multi-way game is you have a multi-way system that is equipped with this set of with this particular equivalence relation that collapses things down to one of the three possible game outcomes. But that in itself is not a completion, or it's not a complete completion, so to speak, or else it wouldn't be a game.
Okay, hold on, because your point is the final essentially this is where it's getting a little confusing, because there's two things we can do. We could say there's a completion, a complete completion would imply
this is why I don't like calling it a completion, because it isn't one, right? It's just an equivalence relation defined on the multi. It's a like I say, a multi-way game is just a multi-way
fine. A complete completion would give only one possible outcome for the game, effectively, i.e. all the, so what we really have is we have a set of equivalence classes. Each outcome in the quotes real game is an equivalence class of final states. It's equivalence class of states. By the way, I would say that in the 3x3 thing, they're not all generational states, because it hasn't actually reached, there's pieces that have not been filled in, right?
Sure, but they're also, yes. But then
I don't understand this game, by the way, because it seems arbitrary who moves next based on the position.
What do you mean?
There are plenty of cases where, well, orange always starts, then blue, but then it's wild for who goes next. And it seems based on the position, who goes next on the
Wait a minute, it better not be. I mean, if this code is written correctly,
actually,
maybe the code is not correct.
If you look on the right there, purple goes twice.
I put some rules for
yeah,
some
okay,
of those
fine.
cases.
So this code is wrong. So let's get it right. Okay, so this is supposed to be, unfortunately, this is not now my code. This is Nick's code. This code was supposed to be alternating players, right? So this should have added an orange only at this step, and it obviously isn't. So is that because the layered graph doesn't do the right thing?
Well, no, because you can trace the evolution edges.
Yeah, it's completely wrong. Well, okay, I didn't write this.
Well, no, it's interesting. It's not completely wrong, right? Because you still end up with the right configurations.
Okay, well, so we should debug this, okay? Okay, important point, states are wrong above. Okay, let's debug that in a minute. But the thing that I'm more interested in, we need to debug that. Is this wrong here or not? Well,
yes, it is. Unless you change the rules of the game. I'm
not trying to change the rules of the game, okay? This is, listen.
Is that what your note that says the following is wrong was indicating? Or is that wrong in a different way?
I think it's wrong in a different way.
Okay.
And this is, okay, hold on. Let me try to find out what was going on here. I don't know what these were. Okay, so Tic-Tac. Okay, let's just try to understand what Tic-Tac association does. Psi. Tic-Tac association is using Tic-Tac function. Okay, Tic-Tac function of k, right? And Tic-Tac association 2 here, yes. Okay, so let's take a look at what it gets as an argument. I don't know whether this is the right thing, but let's just try this. Splat. Okay, let's see whether it needs a list of those. Okay, can we see what it gets as an argument? tic-tac function of k no, I'm sorry, this should have been tic-tac function maybe I should go back to the code that I had, which I'm pretty sure is correct. But let's try this. Okay, so this claims to be the two outcomes that you can get from this. And what it presumably is doing is using, that is probably wrong. That commonest is probably wrong there. Do you see what this is doing here?
It seems so that with that result, 2 is moving twice.
What can, no. What are you talking about? Each one of those is a possible outcome.
Right. I'm assuming player 1 goes first, and then you've got a possible.
Yeah, so this is just wrong. That commonest is wrong. In fact, this idea is wrong. You can't do it in such a way that you can't know what state the game is in, who the next player is, after 2 moves. In this condition, right, you can't tell who was the last to move, right? Because you've got an equal number of 1s and 2s. Do you understand what I'm saying? This code is just wrong.
Right, but as I mentioned,
it could be done by parity. If the total of the flatten is odd, it's player's 1 turn. Otherwise, it's player 2's turn.
How can you tell that?
Flatten and total.
How can you tell, Ed?
If player 1 goes first, then the next move will always be odd, and after player 2 moves, it'll still be odd. Never mind.
Do you mind if I say something?
Yeah, go ahead.
We can just include step number and then use modular arithmetic.
Right.
For sure.
Yeah, ternary. It'll either be 1 or 0 in
All right,
ternary.
let's rewrite this code. This code is wrong, so let's get it right, okay? So what we need to do here, what the heck is that commonest doing there?
As I mentioned earlier, what the commonest is doing is it's ensuring that you still end up with the correct end configurations, right? It will always ensure that both players move the same number of times. It just doesn't guarantee anything about the order. That's why I was saying it's wrong, but it's wrong in an interesting way.
Yeah, all right, okay, fine. So then what we really need is a tic-tac function with a time step here. Okay, and this, okay, so this commonest thing, I'm just not very clear what this is. This is replace part A. Well, that's the trivial thing, right? I mean, we don't even need to do that. We're just saying it's just mod. This thing here all goes away, right? That alternation all goes away. And this just becomes mod t comma, right? It's just mod t comma k comma 1. Is that not correct?
I think mod 3 would be better.
What are you talking about? K is the number of players, right?
Oh, right.
K is the number of players. And this is saying for at turn number 1, you want player 1 to move. So when t is 1, okay, that's sorry. Did I get this wrong? When t is 1, that will be 1. But that thing, comma 1. No, when t is 1, that's correct. That's what we want. T is 1, we want this. When t is 2, we want this. When t is 3, we want this. So it's correct. Right? Yes?
Yes.
Okay, now, Jonathan, let's figure out how to modify this. Okay, so Nick has a version of check win different from mine. So that was my version of check win. I'm pretty sure I had a version of this that worked like this before. So we could either go back to that. We can just, okay. So here we go. So now what do we need to do for this? Jonathan, this is your expertise.
What? I don't understand. What do you mean?
This is making the input to multi-way system.
I know, yeah. So it's just, okay, I mean, the only thing we really have to change is first of hash, is change the state evolution function just to say first of hash plus 1 arrows that.
First of hash plus 1. What? What does the state evolution function get fed when there is a include state number, include step number?
It gets fed the state, which now consists of step number, arrow, state information, right?
Okay, fine. So then what we need to do here is we need to have a
first of hash on arrows, and then that with last of hash in place of the hash.
Right, but I think it would be better to, okay, we have to put in a last of hash in all those places. Okay, all right. Yeah, we were going to need it anyway. Okay, let's just have a function in which we say with t equals first of hash. Actually, we don't even need that. With t equals first of hash and s equals last of hash, right? What did I get wrong here? T equals first of hash. Okay. This is now, the result is t plus 1. Is that right, Jonathan? Is that what we want to do? Is it t plus 1 here?
Hang on. Yes. Sorry, yeah. I thought, yeah.
Okay, now the tic-tac function has a k comma t here, right? Right? Because it depends on the step.
Yep.
Okay, and then we also want to add in here, include step number, is that correct?
But that's not in the association. That's an option for the actual function.
Okay. Okay, now here, okay, so then this, what is win before association?
It's a question of when do you check for wins, right? Before or after the move? At least from my memory of the last live stream.
Okay, so how should we change? We have to rewrite this again with this, right?
Yep.
Okay, and then we'll do the last one here. kind of annoyed that this got wrong because I'm pretty sure I had this right previously, but who's to know? Maybe I got it wrong too. Okay, so this goes to t plus 1 goes to this thing here of s comma t there, right? And this goes to t plus 1 goes to oh my gosh, what's this here? Is that a different hash sign? That's a different hash.
It's mapping over tic-tac function.
Yeah. So that's a different hash there. KTS. All right, let's see if this is right now. Okay, so then here we have to say include step number. And we're full of bugs, and this is all wrong. Okay, let's start debugging this. Okay, so tic-tac association of 2.
You didn't update the rendering functions.
What do the rendering functions need to, what's the story
The
with
state
those?
rendering function takes in a state and renders it. And your state now has 2 parts, and you didn't change hash
Where
2
is the state rendering function here?
in your specification of the multi-way system. So instead, where you say inset plotboard hash 2, you don't say inset plotboard last of hash 2.
Nope.
Well, I mean, just check that the multi-way evolution is actually working. That's probably the first step.
That didn't, oh yeah, right, I need that whole thing.
Yeah. Just change states graph to all states list or something.
Nope, not working. And by the way, Chapin, could you report again the same bug that I just said to make sure was fixed today? Just unbelievable. Just frigging unbelievable. Same mistake.
I got it.
Wait, can you, that state evolution function is returning something in the wrong shape.
Go ahead, what were you saying? Where? Which,
State evolution function is returning something in the wrong shape. Can we actually see what it's returning?
this thing here?
Uh-huh.
What do we feed it? We feed it.
Wait. Tic-tac function is returning a list.
So you want this thing to be mapped over
We can
that.
just thread, can't you?
We could, yes.
Okay, that at least looks
Promising.
sane.
Okay, that was purple. Why did it move with purple there? Oh, because no? Why did this move with purple?
Oh, because we start. No, hang on.
But let me fix these at least.
Which one is purple meant to be player 2?
Yes.
Oh, because we passed in time t, not time t plus 1. So at the first step, it's getting time 0.
Okay. Fine, let's pass in time t plus 1 then. I didn't know first step was step 0.
Well, it's not. The initialization state is step 0. The first step is step 1.
But at that point, it has been.
Well, no. So like the all white configuration is step 0.
Yeah, I get it. Okay, so let's go through these again. See whether we have this right now. Okay, so now this would be, let's say 3 states graph. Well, it's at least looking nice and symmetrical, which is a good sign.
And there are 2 oranges on the last row, on the the last surface, which is a good sign.
Right, so then the final step here would be everything is filled in, and it looks like this. Why is it? I mean, is that just a confusion of the graph drawing thing?
Yes.
No, but this has to be wrong because this is going to. Oh no, that's right. There it is. Okay, so now if we took this,
it might be easier actually to visualize with branchial graphs.
All right, we'll look at the branchial graph in just a second. Okay, so let's say layered digraph. Okay, that looks very dandy, I think. I think that's all correct. Okay, so now here, let's see what this branchial graph looks like now. It's blank. How could that be? Oh, because I didn't put in
You didn't include
step number.
Yes, it doesn't know what to do with an unstepped state. Actually, well, crikey.
That's because we forgot the last there.
There we go. Now, yeah, now at least we can see that they all have 2 oranges.
Right, so okay, so this branchial graph is representing what? Now, this is saying, so by the way, this is now wrong here. And let's try and get this one right, because these will be wrong right now. Lots of things are wrong here. So let's try and get it right before we go back here. Okay, so can we look down? What is tic-tac win association? Is that? Should we just try running that? But this one is definitely wrong here because it doesn't have a t plus 1 in it. Oh no, it does. It has, what does it have a t plus 2? What are we doing here? What on earth are we thinking about here? Well, we can just try this.
When you wrote that, I thought you had a plan, but I wasn't going to ask what it was.
The t plus 2.
Yes.
I think it's just crazy. Okay. Okay, so this was win before association here. What the heck?
Well, yeah. Interesting. Yeah, of course.
Yeah, that's correct.
Yeah. Orange always wins. First player
Right.
always wins. There's no way for orange to lay a square that doesn't win.
Right. Okay, so this picture is wrong.
Okay, so now I agree with you. Now this is a measurement.
Right. But let's now try and get a case. Ed, we need your game help here. Case which is
Adding a sand pile type option, where the people are playing randomly without knowing what the board is, and if they move on the same
no,
space.
Ed, you're not understanding. I want a case. Okay, look, if we do the 3x3 case, all right. If I do 3x3, but can I do? I need a case that isn't as big as 3x3, just because there are too many states in the 3x3 case. Do you get what I'm saying? Is the 2x3 case going to be possible? Do you understand what I'm saying?
Yes, 2x3 would work, and 2 in a row still being necessary for win. That's possible for the second player to win.
Okay, so then this is the case. This is a 2x3 board. Okay, and okay, so now we go. I wonder if this win before association, well, something was winning there. Oh, for goodness freaking sake.
Okay, so on the next step, there should be purple wins.
Right, and so these wins here are orange wins on the vertical direction, right? Right, Ed?
That's what it looks like. I see some places where 2 horizontally aren't winning, so that seems to be correct.
Okay, and this is rather a silly thing, that the winning state then becomes fixed.
I don't think that's silly.
Okay. Well, okay, so there we have it. So there we have 2 possible outcomes. Okay. Now, if we make branch hill graphs of these, maybe we can see something interesting from this. Right, so let's say we look at the branch hill graph after different numbers of steps. Okay, so let's look at let's look at T. Wow, these are more complicated branch hill graphs than I've ever seen before. Okay, what is the interpretation of these branch hill graphs? So, in this case, go ahead.
It's because of the presence of this equivalence relation.
I did something stupid here. Never mind, I did something stupid there. This will make them not look as silly. And I want to take out the aspect ratio. And I want to maybe say, okay, go ahead, Jonathan, you were going to say.
Well, like I say, it's just because of the presence of that equivalence relation.
Right.
If it didn't exist, those islands would remain separated. But they all connect because of that equivalence relation.
Right, which is a very measurement-y thing, I would claim.
Well, yeah, obviously. These are, like I say, they're generational states, they're measurement outcomes.
Okay, but this is what we're trying to figure out, right? I mean, this may all be obvious to you, but it's not obvious to me. Okay, so what we're seeing here is at step, okay, so this is, let's look at the corresponding result for the case where we didn't make measurements, where we didn't have winds here, right? So in this case, what we want to do okay. So let me understand what happened here. So in this case,
like I say, they remain as separate islands because you haven't defined an equivalence relation that connects them.
no, you're right. You're right. But isn't this very much like, I mean, this is very much like quantum measurement, which is interesting.
One thing I've noticed that a 2 in a row diagonally doesn't seem to be a win.
Okay. Okay. Can you make a note of that so that we come back to that? Let's not worry about that right now. It doesn't really matter what the rules are. We're not, this is a decent sized case, right? I'll make a note here. 2 in a row diagonally is not considered a win. I mean, we just get more equivalence classes. I mean, more equivalencing if it was a win, right? I mean, is this always winnable? Is this, or is it going to? There's going to be draws. What is the version of a what does a draw mean in terms of quantum measurement?
It's a third eigenstate.
Okay, fair enough.
If both colors are in every column, that's a draw.
Yes, I understand. All right, so let's go back through this again, understanding what this all means. Okay, so when we look at, for example, this, okay, actually what we really want to do, forget winning here, and let's just look at the case where there's no wins defined here. Okay, big mess. All right. So now, in this picture, we can draw a foliation. We can draw what does it mean? The win is defined by a particular quantum observation frame. Is that a true statement? So if we take a look at this, we're equivalencing these kinds of things here. Actually, let's do the case where we just go 2 steps.
Not a complete frame, as I keep trying to say.
Say that again, what?
It's not a frame. Because it doesn't, the equivalence relation doesn't hold across all states on a particular surface.
Also, I don't think going to 6 moves would look all that bad.
Okay, we can worry about that in a second. Okay, Jonathan, what are you saying here?
Nothing profound, just what I was saying before. It's not.
Why don't you say it again, because I didn't understand it?
It's not an observation frame because it doesn't parameterize the whole space.
Okay, well, how would we make, okay, what is the relationship between, okay, so you're saying for an observation frame, what we need to do is we need to have something that goes across the whole system and somehow weaves its way through different time steps here. Is that what you're saying?
Okay. In the sense that I thought we were using the term quantum observation frame, yes. Because I thought we were saying we have this partial order that's induced by the evolution graph. We want to turn it into a total order, so we define an observation frame. In that sense, this is obviously not an observation frame because we still do not have a partial order at the end. Sorry, we still do not have a total order at the end, because if we did, it wouldn't be a game. There would be a predefined winner. The fact that we don't get a total order is exactly why this is an interesting game.
But you made a different statement, which was that the different wins and loses would correspond to different observation frames.
Well, no, there would be a class of observation frames that perceive orange as winning and a class of observation frames that perceives purple as winning. Just like what's happening here, I don't think is any different from from the ordinary way we formulate quantum mechanics, right? That if you have something like a, I don't know, Stern-Gerlach experiment or whatever that's measuring spins, in reality, there is a huge number of there are a huge number of eigenstates of the universe that are compatible with the first photon being spin up, and there's a huge number of eigenstates that are compatible with the first photon being spin down. But because of how you set up the experimental apparatus, you don't actually care about the difference between all those different eigenstates. You define an equivalence relation that maps all of the first ones onto the spin up measurement outcome, and all the latter ones onto the spin down measurement outcome. That equivalence relation isn't a measurement. It's the precondition for a measurement, right? And that's all that's happening here. We're saying there are all of these different board configurations, but ultimately we just care about purple wins versus orange wins. So we define an equivalence relation that maps onto orange wins, purple wins, and then we perform a measurement, which then, selects one of the two generational states.
Okay, so hold on. See, this is exactly what I was hoping to get out of this discussion, right? Because as the more that we play around with systems that are supposed to be working according to our view of quantum measurement, the more we're going to understand what the heck we're talking about. Okay, at least I might understand slowly. All right, so let's go through this yet again here. Sorry.
Is it all that surprising that generational states for one multi-way system should act the same as generational states in a different multi-way system? That seems...
What do you mean?
That definition of quantum measurement is just a general feature of generational multi-way states. And because wins and losses in games are particular examples of...
I know. But I'm just, it's something, okay, hold on. Let's go through this again. Okay, so the basic claim is, so if we were to actually try and draw, okay, what are you saying here? So this is, oh dear, Chapin, you reported the wrong error. You reported completely the wrong error. That's nothing to do with what the actual error is. Okay.
Okay.
So then I need to report it myself.
Sorry about that. Can you point out what?
No, I'm not going to. I'll send it myself. Okay, hold on. Let me just do this again myself. Yeah. Did you get a screen capture of that resize problem or not?
I did, yes. I'll send it to you.
Thank you. Did you send it right now? Or send it right now, please? Oh, wait a minute.
Yeah, I just sent it. I got a couple of screenshots.
Okay,
so.
okay. I see. Okay, no, you did send the correct report of that one, more or less. Okay, good. Okay. Okay, I'm sorry. I'm being pretty stupid here, but just go through this again. Okay, so in this case, what we're doing is we're saying this set of states.
Well, like here's my general contention, right? That I think a formal definition of an experiment is it's something that maps from all possible configurations of the universe onto a restricted set of configurations that are the measurement outcomes you care about.
Well, or you identify, you make an equivalence class of states of the universe that, okay, so let's have, okay, definition of a measurement.
No, but that's exactly my point. That's not a measurement.
Okay.
I say the formal definition of an experiment.
Okay, I'm sorry, that's what I meant. Right. Definition of an experiment, a quantum experiment. divide the universe into certain equivalents, into equivalence classes, divide the states of the universe into equivalence classes.
Right. My point being that
Labeled by the results of the measurement.
So if you have a Stern-Gerlach experiment or whatever, and you say, I just care about whether this particle is spin up or spin down, that equivalence relation isn't a measurement. That's not the measurement outcome.
No, I understand. That's a definition. So in the case of the game, the quantum experiment is simply the statement, red will win, orange will win if this happens. This is the equivalence class of states in which orange wins.
Right, exactly. And so then the measurement is what you do after that's been done. Once you've equipped your multi-way system with that equivalence relation, which, as I say, the abstract definition of a multi-way game, at least from my perspective, is it's one that kind of naturally mirrors an experiment. That it's a multi-way system that's equipped with a natural equivalence relation that maps onto possible, win outcomes. And then the measurement is the thing you do after. That's the thing that determines who actually won.
Okay, but let's walk through how that works, because what you're saying is taking this picture here, and Ed says we can actually go to 6 steps. Are you saying that, Ed? Ed?
Yes, you can do that.
Oh yeah, you're right. Okay, so here we go. So this is the complete game graph for this game, right? Okay, so now what you're saying is, in here, we can label with an equivalence class all those things which are orange wins and all those things that are purple wins, right?
Right, exactly.
Okay, so then from here, in this picture, we can color this picture by the orange area and the purple area. We can color this picture
And tie area.
by orange and purple wins. Purple wins and ties. Okay, so one way we could do that is let's look at the branch hill graphs here, and we can say, so in each branch hill graph, there is a region of branch hill space that corresponds to each of those things, if I'm not mistaken. Right, guys?
Yep.
So
they may not be nice separable regions. In fact,
let's take a look.
It wouldn't be a very interesting game if they were.
Okay, so we're saying, I see, if they were separable, if there was an event horizon between them, then everything will be determined very early in the game.
Exactly. That would be the point where, your seasoned chess player would resign.
Right. Okay, so in this case, as we look at these, so a failure to entangle is a boring game. Basically, a failure to entangle in the branch hill graph, aka an event horizon, is a boring game whose outcome is very predetermined, right? Okay, so here, let's look at this here. This we can color. So in each of these little things, there'll be a piece that's colored by orange winning, a piece that's colored by purple winning, correct?
Yep.
So we could actually draw that, and maybe we should draw that. In the state rendering function, we can draw that with who is the winner in each of these cases. We can outline these things by their winning status. But in general,
In each of those, it's still possible for blue to win or orange to win.
No, it isn't, because orange already won here.
Right, in that one.
Right, so I don't understand this time dependence, and that probably is not going to be unimportant. But okay, so then this has been colored by orange wins and purple wins. Okay, so that means in our evolution graph here, there are pieces of this evolution graph that are orange winds and purple winds. All right, that is our definition of our quantum experiment, is there are these different regions of the branch hill graph, which are of the multi-way graph that correspond to orange and purple winds. Okay, now what is a measurement? That's an experiment. We've labeled our multi-way graph with these equivalence classes. Now what happens when we do a measurement? What happens when we do a measurement, we're claiming, is that we pick a particular, we freeze on a particular slice of this multi-way graph. But I'm now kind of confused about how that works and how we end up with, we're saying we can only freeze on a generational state. Jonathan?
Yeah.
But I don't understand how that works here, because the generational states are these ones down at the bottom here.
Right.
Okay, so what is the quantum measurement that we would do here? So we've labeled these things for our experiment. Now we want to actually do the measurement.
Yeah.
So what do we do?
The same as in any of these systems. You define a quantum observation frame, you use that to complete. You're done.
Okay, let's walk through it in detail in this case, please, and try to understand how you end up with different quantum observation frames. How do you end up with different measurement results? And then we're going to come back and talk about quantum amplitudes and how that works and how the Born rule works in this case. Right? Because I think we're going to be able to derive, okay, this is my claim, we're going to be able to derive the probabilities for different things to happen in this multi-way, in this tic-tac-toe, from thinking about things in terms of quantum amplitudes and applying the Born rule. That's my claim. And I'd like to see that happen, because I think that gives us a good intuitive way to understand how quantum mechanics works in these systems. So could you describe, how would you describe what happens? So we draw a quantum observation frame, which means in this particular case,
we're not actually measuring the outcome of our experiment here. We're measuring the outcome of something else.
Well, what we would like to measure the outcome of the experiment.
So why aren't we using the experimental multi-way system?
But the experimental multi-way system is this multi-way system. It simply has certain things labeled.
Well, it has an additional equivalence relation defined upon it. That is the definition of the experiment.
But are you imagining? Okay, wait a minute. Now I'm even more confused. I thought the claim was the system evolves as it evolves. There is an equivalence relation which an observer can impose upon the system to decide what happened.
Yeah, that's a measurement.
Right. But the system is just going to evolve as the system evolves.
Yes, that's evolution.
Which is this case here.
Yes.
But then you were saying this isn't a case where the case where we've quote, done the measurement is this case here, where we've applied the equivalence relations and collapsed the thing.
Wait, what? This is just the case where we've defined an experiment. So this is the case in which a measurement would actually make sense, right?
No, but this changes the actual behavior of the multi-way system, as opposed to just in changing the interpretation of what the multi-way system means.
In what way does it change the behavior of the multi-way system? It just mods out by an equivalence relation.
Well, I mean, this state is, what do you mean? It doesn't change it. I mean, you're saying if we were to sort of look, if we were to break apart this equivalence relation, we would get back what we had before. I agree.
Yeah, that's what it means to mod out by an equivalence relation.
Yes, but what you're saying is that what we want to look at is the evolution in this system where we have applied the equivalence relation. as opposed to applying the equivalence relation afterwards.
I'm asking what you're asking. If you're asking, how do we apply a measurement in an undifferentiated multi-way system with no experiment defined, so we're just measuring a single microscopic eigenstate of the universe, then obviously, then the previous multi-way system you showed makes sense. If you mean, how would we apply a measurement in a multi-way system which has an experiment actually defined?
That's what I'm talking about. That is the case that I'm interested in, yes.
Yeah, so then this is the one that's relevant, right?
Okay, then can you walk through your interpretation of this?
Yeah, sure. So then we pick a foliation, which is a time-ordered sequence of equivalence relations between elements.
Wait. We're going to pick a foliation, which in practice in this picture means like this is what we have right here is some kind of cosmological rest frame sequence of configurations, right? Where we just say successive time steps are just the layers that we show here, right?
Yes.
An alternative is that we're picking some more elaborate thing where we say, we should actually try and actually pick a foliation and do something with it. But okay, so what do you think is an interesting foliation here?
Well, I mean, just a flat one that's tipped slightly would be fine.
Why would you like to tip it?
So we get a measurement outcome.
I didn't understand that, but keep going. Okay, keep
going.
Well,
no, obviously, if you just have the cosmological reference, again, as with any of these multi-way systems, if you just pick the cosmological multi-way system, you'll end up defining an equivalence. You'll end up just equivalencing between orange and purple wins. So your measurement outcome is that both win or neither win. Right? There's no.
So your point is, if we think about a foliation, so I'm still trying to understand this. If we think about a foliation here, and looking at, let's see if we can draw, yeah, this guy. Is this it? Yeah, this is it. This is the. Oh, I see. I probably want to go to 6 here, and that way I'll see what's going on. Okay, so if we look at it in terms of these branch hill graphs, the foliation will select certain pieces at one of the, this is the branch hill graphs in the cosmological rest frame, right? Now, in a tipped foliation, we will get different branch hill graphs, right?
Right.
So what aspect of the branch hill graphs would you like to see to be successful in your measurement quest?
Well, okay, so the point is that, generally with one of these multi-way systems, what's happening is you define a foliation. It's some time-ordered sequence of equivalence relations equivalence classes, sorry, I should say, between elements or between states. And then which states lie on the same hypersurface, i.e. which states exist in that within that equivalence class, then tells you what completion rules to add, right? So basically you're saying, I want to treat things that appear on this hypersurface as being equivalent. So I define a set of completion rules that treats them as equivalent.
Yes.
Right. So then depending on, so if you sculpt out a cosmological reference frame, okay, obviously, for the game case, as we discussed in the last live stream at length, this is a bit screwy because you have a turn-based game. So actually, orange wins. The orange generational win state appears first, but only because orange played first. It's not like a genuine effect. So actually, you should probably consider the case where you have pairs of branch hill graphs stacked on top of each other, if you see what I mean, right? Because you actually want to consider not turns but plies as being, or in other words, you want to consider the turns as being simultaneous. But anyway, as long as you admit to that slight subtlety, all you're really asking is, can I construct a reference frame in which all of the current states lie on a hypersurface along with the orange win state, or can I construct a hypersurface where all of the current states lie along with the purple win state, and then those correspond to observation frames in which one would see orange and purple winning, respectively.
Okay, so let me see if I understand what you said here. So your first point is somewhat weird that in the game there is not time invariance because of back and forth moves, basically. So you're saying if we did both moves at the same time, then we could avoid this.
Right, right. So assuming this the simultaneity case, then in the cosmological reference frame, both win states appear at the same time, right? They both appear after whatever.
Yep. Yep.
But if you were to tip your reference frame to one side or the other, the orange would appear before the purple, or the purple would appear before the orange. And so then, if you're going to use that reference frame to define a completion, to define a set of states to treat as being equivalent, therefore you would say, well, all in the first case, all states have led to orange winning, or all states have led to purple winning, and therefore you've defined a single definite.
All right, I understand what you're saying.
You can fake that by doing only every second move.
Walk me through that, Ed.
That table you've got right there, instead of T6, do T6, 2, I think.
Although that's slightly subtle because the branching graphs are meant to show one step back, but
that's right.
It should say
We don't have two-step branchial graphs here, do we?
No, we do not.
But we could do this also by just running two versions of the tic-tac function. We could just run the tic-tac. We could compose two tic-tac functions.
Exactly, and as long it gets a little bit screwy with the step numbers, but yes, I think that should work.
Well, we could just blow away the step numbers if we did them both at the same time.
Is that true?
Sure. It doesn't care about the step number because we're adding a purple and we're adding an orange. Well, let's write a double step version of this.
But which one goes first? Even within that, which one goes first does matter, doesn't it?
Maybe it does.
Not unless you check your win after that, after each ply instead of after each move.
Okay, but so here let's do a double move, the double move case. Okay, so this is double move win before association. And so the double move here would be this tic-tac function wants to be applied twice, if I'm not mistaken. And then we do a check win. Oh, we might have a double win then, mightn't we? Do you understand what I'm saying?
Yes, that's possible. In that case, it would be a tie.
Well, who knows what our check win function will do there. This code will have to be probably rewritten, but so here, what I could do is, first of all, in this, I am basically saying tic-tac function of that hash /at, and then I probably want to catenate there. Do you think that's right? Oh no, T+2 here. Oh, this is going to get kind of screwy. Okay, there's a T+2 there, and there's a T+2 there, I claim. Okay, so let's see if that comes out with anything reasonable. So we want this case here. So this is now tic-tac, win before association, blah, blah, blah. And then we want Well, let's see what happens.
Hey,
Ooh.
that doesn't look too bad.
You think it's correct?
Well, orange and purple win at the same time, which is a good sign.
That's a good start. All right, let's assume it's correct for now.
Well, it doesn't look obviously wrong.
Right. Okay, so for our purposes of explaining what's going on, this is sufficient. So what you're claiming then is that if our quantum observation frame winds its way like this, okay, so that purple is first in time, then by...
So, I mean, the fundamental point is, right, that in practice, you are never going to actually be in... So, you know, okay, one of the idealizations of this formalism is that if you happened to be in the cosmological reference frame, you would succeed in seeing both things happen, but, you know, both winds occur. But in practice, you're never actually going to be in the cosmological reference frame. You're going to be slightly tipped in one direction or the other. So you will see a hypersurface in which all current states are treated as equivalent to an orange win or a purple win, but not to the other.
Okay, so let's walk through that for a second. So what you're saying is, in practice, the quantum observation frame that you pick, nothing to do with spatial frames, the quantum observation frame in which you happen to live, and I don't know how you pick. So, you know, your claim has been the quantum observation frame is a question of your choice of where constant quantum phase is, in the same sense as your choice of where constant clock phase is in physical space.
Exactly, right. And the point is that, I mean, we call it a choice because it's a free parameter, but it isn't an observable quantity, and it can't be an observable quantity. And in effect, that's kind of what Bell's theorem is telling you, or that's an aspect of what Bell's theorem is telling you.
Is what? Explain.
So the fact that the outcomes of quantum measurements appear non-deterministic is related to the fact that your quantum observation frame is not itself an observable quantity.
Well, in other words, put a different way, the hidden variable is the quantum observation frame.
Exactly.
It's not a state of the... That's a very interesting way to put it, which maybe you've understood for months, but I hadn't understood.
One weirdness here is that there aren't enough tie positions.
Okay, Ed, there's a bug in this code. Go figure out what the bug is. This code is good enough for a picture. Okay, it's probably not correct for what we thought it was, but that's okay.
Right. So anyway, because the observation frame isn't a state, it's not a physical aspect of the universe. It's an aspect of your own internal representation. It's not bound by the Bell's theorem argument.
Okay, this is a very good point, Jonathan, which we should have understood a lot. Well, maybe you've understood this for months, okay? This is the answer to why the violation of Bell's inequality has nothing, why this is in no way like hidden variables, is, first of all, the full state of the universe is, the full state of all possible histories of the universe is represented by the multi-way system. But the point is that you're saying that, the notion of probabilities now devolves to a notion of selection of quantum observation frames,
right?
Which we kind of already knew.
Exactly. It's a Bayesian version of probability, right? You're saying if I knew, okay, if my quantum observation frame were observationally accessible to me, then I could predict the outcomes of every quantum measurement, which would obviously violate Bell's inequalities and so on. And so the point is, I can't do that, right? That there is a hidden variable, but it's not a hidden variable of the universe. It's a hidden variable of my observation frame.
Okay, let's internalize that a little bit more. So let's think about that in the relativistic case. In the ordinary, you're saying the choice of simultaneity surface.
It's just the equivalence, right?
So again, what?
In the relativistic case, it just reduces to the statement of the equivalence principle.
Walk me through that. So you're
in relativity. I see a particular configuration of clock evolutions or whatever,
Right.
I
Was
try
it a
and
gravitational field or was it a choice of reference frame?
Exactly, yes. And the whole point of the equivalence principle is I can't disentangle the two. So in other words, my reference frame is not observationally accessible because it's not that information is not extractable from the underlying geometry of space-time. And all we're doing is we're saying, well, if our foliations of the multi-way system are like the foliations of the causal network, the equivalence principle should hold in the multi-way case as well. And that's basically where non-determinism of measurement comes from.
Okay, let's walk through that another time. Okay. So what is the analog of the equivalence principle? So the equivalence principle, okay, so the claim is arbitrariness of reference frames or what is the right term? It's the non-physicality of reference frames is basically a statement of the equivalence principle, is the claim.
Yes, or I guess not. I mean, it's also, I mean, it's kind of a statement of general covariance as well, in some sense.
Yeah, general covariance, equivalence principle, whatever, they're very much related. So,
right.
So this is saying, that is saying, there is no difference between a different coordination and there's no observational difference between a different coordination and a different gravitational field. A different space-time geometry / gravitational field. Okay, so what's the analogous statement for quantum mechanics here? What is the analog of this? So I think the analog of this, I mean, this is the multi-space story of, you know, what is curvature in multi-space? And that's what we're talking about here, right? Because curvature in this curvature, chunk, you know, a frame here is giving us different, you know, different measured results. Just as in the relativistic case, we would, you know, we say the clocks are running at different speeds or whatever else, depending on our frame. So, Jonathan, what would you, in this case here, we're asking, what is the analog of this gravitational field idea?
Well, it's just the geometry of the multi-way system, the geometry of the branch yield space.
Yes.
Right.
But what's our interpretation? So, I mean, the geometry, you know, geometry of branch yield / multi-space. That determines the particular coordinatized measurement that we, you know. Okay, so here's the question. Okay, in a sense, measurement is about coordinatization. That is, the reason we think it's this result rather than that result is because we've picked a coordinate system in which this is the answer. So the obvious question is, there are generally covariant statements that we can make in relativity. What are the analogous generally covariant statements that we can make in quantum mechanics?
Well, okay, again, this may differ from your way of thinking about it, but at least in the way that I've been formulating things, they are basically direct analogs of the statements you would say you would make in general relativity, right? So in GR, the reason why tensors are useful is because tensor calculus is exactly kind of the mathematics of coordinate of non-coordinate specific statements, right?
Non-coordinate specific. You mean the whole tensor as a big blob, as opposed to the tensor with its legs specifically laid out?
I don't.
I mean, by the time you've got, we're talking R mu nu, where we don't say what the mu and the nu really correspond to in terms of coordinate systems.
Right, exactly. So any tensor equation doesn't depend on coordinate systems. That's what, that's why.
Yeah, right. Right. Yes.
And so you can also write similar tensor equations that apply not in Lorentzian manifolds as in spacetime, but for projective Hilbert spaces, which is the quantum mechanical case. And so then you can formulate kind of the analog of a generally covariant theory of projective Hilbert spaces. And as I say, at least the way that I've been thinking about things has been in terms of interpreting, evolution of branchial graphs in that context.
Well, that's lovely. But then, so what is the coordinate-free? What's an example of a coordinate-free equation that you can write? Like our friend, the Wheeler-DeWitt equation. Is that writable in that form?
Well, we don't know. This is something Xerxes and I are working on, but if this way of thinking about it is correct, yes, it had better be coordinate independent.
Okay, so the claim here would be
the path integral is an obvious example, right? Because the path integral is just, it's the Einstein-Hilbert action, but
okay, is a coordinate independent, can be written, e.g., should be able to be should be able to be written as a tensor equation. Okay, so what is the analog? Okay, so the path integral quotes as a tensor equation. What does that look like? What does it mean to do that? So that's the differential version of the path integral. That's not the path integral. That's more the Schrodinger equation, right? The path integral is the sort of integral equation for a geodesic.
Well, like I say, in this way of formulating things, the path integral is the same statement as the Einstein-Hilbert action. So then the point is,
right? Okay, so so what you're saying here is that the path integral,
upon extremization, it yields a tensor equation, just like extremization of the Einstein-Hilbert action leads to the Einstein field equations.
Right. So is an extremization. Okay, so the path integral, the standard, Lagrangian action principle. The hell is it called? Lagrange's equations and so on. Is an extremization of an action. And then the path integral is the quantum version of that.
Exactly. And so just as in the relativistic case, you would have your space-time Ricci scalar that whose integral you're extremizing. And the point is the analog of the space-time Ricci scalar for the multi-way case, again, in this way of thinking about things, is the Lagrangian density. And so you get exactly the path integral. Right.
So normally we'd have an R square root of G in the relativistic case.
Exactly.
Although, wait a minute, what does it look like when you have T mu nu in there as well?
So then there's an additional matter field term.
Basically R plus T square root of G.
Right.
First approximation, with some 8 pi's thrown in for good measure. Okay, so then in the path integral case, what is the analogous statement? What is the analog of the R in the path integral case?
The Lagrangian density, or at least
well, that's the T. That would be the analog of the T.
Well, maybe.
Is it obvious that there isn't an analog? I mean, the R case, the R there is a statement about curvature in branchial space.
Right, exactly. So the point that I'm making is that, when you know that this is an Einstein, in the relativistic case, the Ricci curvature and the energy and the matter field term in the relativistic Lagrangian density are known to be related, right? That's kind of what the Einstein field equations say.
Yep.
There is a similar thing that you can state about the Fubini-Studi metric when you formulate it for projective Hilbert spaces. that there's a relationship between the curvature as described by the Fubini-Study metric and the Lagrangian density. And so just as when you're deriving the field equations, you can treat the R and T terms as being part of the same relativistic Lagrangian, as long as you have appropriate coupling constants, you can do the same thing here.
Okay, so let's walk through that. Let's walk through that more carefully. So your claim is, okay, first point, Einstein equations, relate T, R, and T. Therefore, for an extremization, well, I don't really know what you're extremizing over. If you've already decided you related, okay, well, therefore, for extremization, you can extremize them together, is the claim. Is that right? I mean, why isn't that tautological? Because the fact that, let's see, is that what you're claiming? You can extremize the two together because you've already solved, but to get the relation between R and T, you have to make an equation of motion, which you get by doing the extremization, don't you?
But you already have the extremization for the R case.
You're saying for T equals 0, you do the extremization. I'm confused here. I mean, the equation of motion that give you the relationship between R and T can be thought of as the result of extremization.
Yes.
So I don't see how you can then use the equations of motion to substitute into something that you're then going to extremize.
You're not. Okay, right. In the ordinary derivation of this, right? So you are the way that this is constructed is you start with your relativistic Lagrangian density, which is just a sum of the gravitational Lagrangian density plus a coupling constant times the matter field Lagrangian density, right?
Yep.
Then when you do the relevant traces, the gravitational part reduces to the Ricci scalar, and the matter field part reduces to an energy momentum term. From that, you can deduce that they are coupled via the Einstein equation and so on.
Yes.
Once you know that, if you wanted to do that derivation again, you now know that it's kind of, you don't need to treat R and T as being separate, right? Because they're related by that equation.
Yeah, I kind of get it. Okay, but so you're claiming in the quantum mechanical case that this R QM case, there is an R somewhere in the Fubini-Study metric of Hilbert space.
Right.
But you can basically you can apply the equation of motion basically to get rid of it. And now you're extremizing with respect to T. That's not right. That's not right. You're trying to derive the curvature of the Hilbert space, aren't you? Isn't that the output that you want? Isn't the output that you want the curvature of the Hilbert space that is going to essentially give you the values of quantum amplitudes?
But this is the whole point. It doesn't matter whether it's curvature or not. I completely don't understand what's going on here. So in ordinary general relativity, okay, for instance, with something like a cosmological constant, because we know the equations of motion, we know you can treat the cosmological constant as being a curvature term, or you can treat it as being an energy momentum term. And it doesn't matter which one you do. And so when you do the extremization, there are some cases where it makes sense to treat everything as being a curvature term, and there are some cases where it makes sense to treat everything as being an energy momentum term, and there are some cases where it makes sense to have.
But when you say we're doing the extremization, the goal of the extremization is to compute. You can think of it as being to compute R mu nu as a function of position.
Or T mu nu as a function of, it would only be to compute R mu nu as a function of position if you shifted everything to be curvature.
Right. Yeah, I mean, okay, fine. So you're saying it is to compute something as a function of position. Right. So similarly, in the quantum mechanical case, the analog of that is to compute something, and the something in this case is going to wind up being It's some kind of measure thing that you're computing as a function of position in branch Hill space. And that is giving you the quantum amplitudes, basically.
Right. And so just as in the relativistic case, you can shift everything to make it a curvature term, but the reason I prefer not to think of it that way is because I don't have a good intuition yet for what Fubini-Sturdy curvature really is. I mean, it's related to entanglement monotones and things, but it's still a little bit subtle. It's much easier to think of things concretely in terms of Lagrangian density. So that's kind of how I prefer to formulate it.
But the Lagrangian density, I don't understand. You're not computing. The Lagrangian density is a given. You're not trying to compute it. Or you might be trying to compute the density part of it. The Lagrangian, that's saying, which is again very similar to this curvature question. You're trying to compute, this is some complicated space whose slices we've just got wherever they were. We've got, actually, let's get we didn't get the, where did we get this? We want the, what do we want here? We want the branch Hill slices of this creature, right? Let's look at the branch Hill slices of this creature. Oh boy. That's pretty weird. Okay, so in that state, is that a complete graph? Probably. Okay, interpret what's going on here. So this is, boy, what the heck is going on here? This is saying, in a tipped, if this thing here you're claiming was not a cosmological frame branch Hill graph, but was a tipped branch Hill graph, I would see one wind state and not the other wind state here. Is that your claim?
Right.
And then in reducing, you're saying that insofar as I say, walk me through this. So let's say we've got this slice and we say, this is the state of the universe now.
Yeah, so
This
in the relativistic case, the analog would be, I have two space-like separated light pulses, and I'm going to set up an experiment in such a way as I say, if I see light pulse 1 first, then I'll say the measurement outcome is 1. If I see light pulse 2 first, I'll say it's 2. And then the point is that there is a reference frame in which the two light pulses are simultaneous, but the probability that I will pick that one is vanishingly small. In most reference frames, I will see one happen first or the other. And I have some degree of, because of gauge freedom, I have some degree of freedom to select which one it is.
Okay, fine. I understand that. But now, physically, it's like you did that measurement, but now the state of the world is such that eventually you get to the other measurement. In other words, if you just keep going in time, you'd get to the other measurement result.
Yeah, except that, again, at least in my way of thinking about things, the key thing that differentiates the relativistic and quantum mechanical cases in these models is that in the quantum mechanical case, the foliation doesn't just define simultaneities, it crucially defines completions. So if you've got a hypersurface in which there's a bunch of states of the universe and an orange win, and we're going to say, let's treat all of these as being equivalent, now we've equivalentized everything to the orange win state.
Right. This is the theory. This is the theory. We only think one thing, so to speak.
Right. And then just like in the multi-way system, just like in this version of the multi-way system, once you have an orange win state, it remains an orange win state indefinitely.
Well, and the reason for that is because in our perception of the world, we think, we are only capable of understanding that one thing happened. And therefore, what's happening, what we interpret this to be is, yes, the orange won. I'm still trying to wrap my brain around this idea. So the basic point is that as soon as you try to imagine that something definite happened, you are forcing the world into this completion. I mean, okay, let's walk through this again. Basically, the point is the very perception that something definite has happened. I mean, this is the collapse of the wave packet story, explained in a very different way. Because this is saying the reason that the wave packet is collapsed and nothing more happens, because that's the critical thing in quantum measurement, is that sort of nothing more happens. The quantum evolution is over. So you're saying the reason the quantum evolution is over, well, explain, what would you say? Why is the quantum evolution over? So the completion is made by virtue of our brains, which are themselves multi-way systems. Somehow we are conceptualizing that as a definite outcome, right? Now, having conceptualized as a definite outcome, we've essentially knitted those threads of reality together, and we don't let them unknit. But can you explain that further?
Maybe. I mean, it's just an equivalence class, right?
Well, yes, but it's an equivalence class that is constructed by our brains.
Yeah, sure.
It's an equivalence class constructed by our brains because the way we choose to describe what's going on, in reality, there are many paths being followed, but in the way that we choose to talk about what's going on, we're saying there is a definite thing that happened. Now, I don't know. Right, and that's and having completed, you can't break the equivalence class open again. And that's why that's essentially the collapse moment, is that completion.
Right, exactly. Because that equivalence class has a canonical element, which is the generational state. Right.
Right.
So either the purple win. And so once you've reduced everything to that canonical state, there's nothing else that can happen.
Well, I mean, the statement there's nothing else that can happen, I don't understand that. I mean, you could go on with as we can see from this picture, you could perfectly well go on with evolution after this.
Well, okay, so this is where it's helpful to distinguish between two things. Do you mean how does it work formalistically in the multi-way system, or how does it work kind of philosophically in our definition of an observer?
The second thing, philosophically, how does it work? But actually something intermediate between those. How does it work mechanically for us as observers?
Well, that's fine. I mean, so you're just saying, okay, I've constructed my equivalence class so that I see orange wins. So now anything else that happens that cannot be made consistent with that view of the world is essentially ignored. That's the, sealing off.
There's a certain unfortunate cultural resonance here, which is, by the time something happens in the world that is not consistent with the view of the world that you've developed, so to speak, you assume that it hasn't happened.
Exactly.
Yes, right, which is unfortunately, anyway, never mind.
Yes.
Which denies objective reality at all levels, so to speak.
Our project represents some kind of post-measurement effect for mainstream physics.
Yes, I suppose that's right. It's a right. It thought it already had an answer. Well, it didn't actually. It really didn't. At various times in history, it thought it had an answer, but then the thing opened up again. The equivalence class broke apart. But in any case,
So and that's what your the nice pictures in your technical introduction with the constructing reference frames that seal off a particular generational state and basically fighting off causal edges that conflict with it and so on. Right. That's ultimately what those were representing. We're saying we're going to sculpt out. We're going to construct this equivalence class that reduces everything to this one canonical generational state. And we're just going to sculpt the reference frame in such a way. We're going to sculpt the equivalence class in such a way that basically anything that's not consistent with that state is ignored. And that's ultimately what a classical measurement outcome means.
All right. Okay. Here's the final exercise, he says. Let's understand this picture in terms of quantum amplitudes, in terms of because one of the issues is in this branch Hill space. So we have a nice picture here that shows that different, I mean, unfortunately, they ended up very close together in this particular rendering, but conceptually, these are some distance apart in branch Hill space. And we could draw different foliations in which we would see only one of these happening first, so to speak. See, one of the things I find interesting, right, which is not really something I had internalized at all about quantum measurement, is, first to be found is the winner of the measurement. You know what I'm saying? In other words, these quantum observation frames relate time to quantum measurement in a way that time has never really been, time is not really a factor in the standard theory of quantum measurement. Whereas what we're saying is, whoever was the first generational state to be reached is the winner.
Yes, I mean, in effect, our definition of a quantum observer is is a time, is the sequence of measurement operations in time. That's ultimately what defines different observers. Sure,
but different sequence. But the whole point is, it's very much like one of these games where the winner, the first to reach the finish line wins, so to speak, and then all else is over. Right? Because that's what's being said here. By the time the foliation that you are using, it's all a little bit, so explain why different observers like you and me conclude that the same thing happens.
Well, do we? If it's the same experiment, we do.
Right. Well,
but if we perform identical experiments, but we have different observation frames, we won't.
Yeah, it's completely different. If we're just doing copies of the same experiment, all bets are off. But if it's the very same experiment, we're looking at the same electron.
Right. But if you look at it first, and are you asking if you look at the electron first and see a particular outcome, why did my measurements then concur with your outcome?
No, I'm not very concerned about that. I think that's already defined this quantum observation frame.
Right.
No, I guess what I'm asking is, if we see these results simultaneously, well, or maybe that just never happens.
Yeah, right. I mean, again, if you think of the analogy, or at least for me, it helps to think about the analogous relativistic case. If two people happens to observe the same pair of light pulses with synchronized watches, but with different velocities, they could end up not concluding that the same sequence of things happened.
Right.
Let me suggest a slightly different game.
Yes.
So go on an infinite board. You could look at a position at any time and figure out who was winning based on the fields.
You mean what was nearby?
Right, because there's some regions that were going to be dominated by white and some dominated by black. And based on the total measurement of the fields, you could figure out who was winning.
I think that's a much more complicated case than the case we're looking at here. I mean,
yeah, it's unsolvable.
But I think that feels much more like a hidden variables model of the world, whereas this is really not. This is something where the very definition of the measurement frame. But we're going to run out of time here, and I really want to come back to this quantum, the interpretation of branch Hill space, coordinatization of this branch Hill space.
By the way, sorry, I mean, just quickly to finish off the previous point. I mean, you probably already realized this, but why you and I assuming that we didn't perform the measurement exactly simultaneously, The reason why you and I have to come to the same conclusion about what happened is because the branch of the multi-way system where I come to a different conclusion about what happened is one of those branches of the multi-way system that you cannot make consistent with the measurement outcome that you saw. So the version of me where I saw something different happen is one that is fought off by your choice of observation frame.
Right. So that observation frame has eschewed that particular outcome. Right, but so coming back to this, and coming back to the question of, in this picture, right, can we actually assign complex numbers, coordinates here, to these different things, and what would it mean to do so? And then if what we want to work out, okay, so here's a really basic question. In this particular game, there's a 50% probability of purple and orange winning, okay? We could clearly, we can, I don't know how we would do it. Ed can tell us how to do it. We can bias the game. Maybe we put down one orange square at the beginning. We'll bias the game to change those probabilities. Okay. So now what I want to do is I want to derive that result, the different probabilities of orange and purple winning from quantum mechanics. See what I'm saying? Because here it looks like those different probabilities are, if we just do path weights getting to these points, right, we'll get some result. That will give us, I'm trying to understand, okay, like for example, let's say we want to get quantum interference. Can we get that in this case? Or do we need how would we get quantum interference here? Or does that...
We do have symmetry breaking with this particular code.
Well, that's true, yes. Yeah, that's true. But Jonathan, do you understand what I'm saying? I mean, can we label these points in branch Hill space by, can we assign a phase to these points in branch Hill space?
Yeah.
And so what if we do that? So what does it mean to say, what's that?
As we discussed last time, right? It's basically a score.
Well, the distance between these things, can we go through this in a little bit more detail? Okay.
Yeah.
So go ahead.
You have two possible generational states. And if we assume without loss of generality that they lie on opposite sides of branch Hill space, then your phase information is encoding how close a particular state is to the purple win state or how close it is to the orange win state.
Mm-hmm.
So it's basically a score.
Okay, but how do you use that in computing? Okay, how do we actually compute? How does that help? And look, let's say we're trying to do quantum mechanics here. We're trying to compute probabilities. I mean, it'd be lovely to see, the Born rule mechanism as we do the completion, see this idea of the, of the square of the amplitude coming in from doing the completion. Is that going to happen? Can we see that in this case? So let's say we have not done the completions necessary to identify what we've got in our picture up here. Okay. We've picked a state, a reference frame here. Am I making sense? I'd like to see the actual quantum formalism show up in this system, which I'm pretty sure it can.
Sure.
Well, but can you explain it? I mean, do you see how it works?
Which part? When you
say write down. Okay, my question is: let's say you're trying to compute the probability. What would be a typical quantum computation? It would be the probability for orange to win or purple to win in a biased game of this type, let's say. Is that a reasonable quantum computation?
Sure.
Okay, so now one way I can get the answer to that is by pure path counting, right? In which there's no notion of branch Hill location. Doesn't care about the branch Hill location.
Right.
So I think that is not insofar as you can get the outcome, you can get those probabilities by pure path counting, you neither have the Born rule, nor do you have any relevance of quantum phase.
But
So my question is, what's the minimal case?
those probabilities are not quantum probabilities. Those are probabilities assuming you have a stochastic path through this multi-way system. What are the different, what's the probability of seeing
All right,
each
okay, so what is the quantum version of that? If you're making that statement, you're saying that there is you can compute the path weight by just doing the standard formulas for sums of path weights. Right? You can compute the path weight to get from here to here relative to the one to get from here to here.
Yeah, right.
Okay, so those are some numbers, right? One has total path weight 100, the other has total path weight, I don't know whether it's sufficiently symmetrical, whether it's also 100 or whether it's something different.
Okay, we could find out.
How do we find out? Let's just find out here. Let's
Include state path weights.
and then how do we do the rendering? And then I say, I say graph with vertex labels arrow automatic. Yeah?
You don't even need graph. You can just say in resource function. No, it's no. Vertex, not vertex. Vertex labels vertex weight.
Okay, so this is telling us, so let's say draw versus one of those equivalence classes. So this is giving us the relative weight, relative path weight going to each of these outcomes. So what do we conclude from this? And I unfortunately am supposed to go to some other meeting. And
anyway, so the point I was making, which is not a very sophisticated one, is just that these obviously can't be quantum probabilities, for the simple reason that, okay, basically, if you interpret the multi-way system as just some stochastic system, right, where we're just going to play tic-tac-toe by following something randomly here, then the multi-way system is giving you some statistical ensemble of those different strategies, and then these are exactly the classical probabilities for each ensemble. But we already know in the standard formalism of quantum mechanics that that's not how quantum probabilities work, because you have in QM you have quantum probabilities, which are the probabilities of measurement outcomes that you get by squaring the norms of the amplitudes, and you have classical probabilities that appear in, say, density matrices. And the point, the very point behind things like quantum mixed states is that you can have situations where the quantum probabilities and the classical probabilities interact, and they're not the same. You can't treat them as being equivalent.
Fair enough. Okay, so then what is the quantum probability version of this? So assume no mixed states. Assume you've traced nothing out.
Right. So assuming there's no ensembling going on, then you're just collapsing. If there's no ensemble, then you're collapsing everything down to just a single path, and so you're composing all of the weights. You're basically you're taking the measurement outcome you want to see, and then you're applying you're forcing all the other possible paths to lead to that particular outcome. That's what the completion is doing.
Mm-hmm.
And so you're not, rather than just taking the number that you're seeing here, you're taking the number and you're doing this arithmetical operation to it, which is adding to all of these other path weights to it. And it's that operation that ultimately will give you the Born rule.
Wait a minute. What are you adding to what? So we've got 236 here.
Uh-huh.
Okay, so what are you proposing to add?
Well, so, okay, maybe it'll be clearer if you say include state weights goes to true rather than path weights. And then we can see the normalized version.
Would you want to include what?
State weights.
Include just state weights?
Yep.
Something beeped there, but that's okay.
Uh,
The heck is this? That's something where it's given an error.
oh dear, hang on.
That's probably because of this equivalence classing here. It thinks there are 9 states, but it's been equivalence together.
Yes, I think you're right. It doesn't like that. Okay, fine. Well, just look at the thing after 2 steps. That suffices to make the point. So,
Okay.
so those are your normalized amplitudes. Oh, it's still beeping.
Well, close enough. Okay, we'll worry about that. We'll separately worry about that. Okay.
Something's going wrong there. But anyway, so then in order for you to measure a classical outcome, you need to have some way of projecting everything else that goes on onto the eigenstate that you want to measure, or the measurement outcome that you want to see.
Mm-hmm.
And so when you do that projection, you're taking your weighting as you're seeing it, and you're adding in a whole bunch of other weights.
Which other weights are you adding in?
Well, the weights of all the other possible paths.
Well, let's be concrete. So we're getting to here, right? And we've got a bunch of paths. I mean, the ordinary path weights are just counting the number of possible ways that we can get to this place, right? What are you saying that's different than that?
I'm saying if you perform a completion, you're then applying this arithmetical operation that's projecting all other possible path weights onto that state.
So but by doing a completion, what we mean is we're taking what would be 2 different paths and we're conflating them into a single path.
Yeah.
But what do we do to the weights of those 2 paths? So in fact, what we've done as we do that is because we've added this completion, there's more crisscrossing. As you know, for every diamond, there's also a thing that goes across the middle of the diamond.
Exactly, right. So and if you assume that the path weights compose additively, then you recover the Born rule, because
Right. Well, that's a very recent and interesting claim, Jonathan, which I agree seems to be correct.
Because for every path that, precisely because of this diamonding argument, right? That because you're basically adding in another multiple of the weights for every pair of edges.
Right. See, but that's really interesting. I mean, so that will be saying in this case, what we would be getting. So it's an alternative way. Is it? Are we going to get the same result as the classical computation of the tic-tac-toe probabilities? So the claim would be by looking at completions and the Born rule, we would get the same result as the classical ensemble calculation.
I don't think so. I think the point is we would get different results. That's why, statistical ensembles and quantum superpositions don't behave the same way.
No, they don't, but they often behave, often in the limit, they do behave the same way.
Maybe, and okay, obviously unbiased tic-tac-toe is obviously one case where they will behave the same, but biased tic-tac-toe I'm less confident about. I don't.
Okay. Well, is it obvious? Why is it obvious that unbiased tic-tac-toe
because if you have 2 eigenstates, and if you only have 2 eigenstates of your measurement of your observable, and they both have the same weight, then they both have the same amplitudes, then they both produce the same probabilities.
Right.
But that's a very special case, and that doesn't generalize.
Right. But so I unfortunately have to go to this other meeting, but I mean, again, I'm still, look, again, one of the reasons I thought it would be interesting to look at this is because of our quest to coordinatize branch Hill space, to say what are the reasonable coordinates to give. And your claim is that the essentially score difference. I mean, the claim would be some kind of relative score is somehow related to relative phase. Or phase, no, actually, score difference is related to phase difference, is the claim.
Right.
But how can we see what is the implication of that?
Well,
That's saying, go ahead.
It's quite a direct thing, right? Because what you're saying is, so suppose you try and construct one of these observation frames where you say orange wins, and I'm going to fight off everything where purple, I'm going to ignore anything where purple wins.
Yeah.
Right? Then what you're basically saying is I'm going to, I'm projecting into this phase region, right? And anything with which has a phase that's too different is going to get ignored.
Right.
Which is basically a destructive interference claim. There's some subtlety there, but that's loosely speaking what's happening.
I wonder whether we can see something which has a phase that I mean, like in the case of the double slit experiment, the kind of the interesting claim, still somewhat disputed by some, but I think pretty convincingly correct, is this fact that the phase wraps around. Can we see that in this case? Can we see a case, and this is perhaps an Ed question, where the scoring function, as you go further away in branchial space, the scoring does not monotonically decrease as you simply move apart in branchial space?
Well, just to quickly address the previous question, I mean, that's about when you try and take your, if you try to take this thing and then project it onto the space of the board itself, if you try and annotate the board with this phase information.
Yes.
Which is a slightly different case.
Okay, wait. You're saying
that's the double slit case.
Right, but what does it mean when you, I see. So the basic point, so the analog of double slit is where did the win happen?
Exactly.
On the board. And so the claim would be the analog of interference, of destructive interference, I bet there's a direct analog here. I bet there's a really direct analog. That there's a zone in which, like if you're on the periphery of the board or something, it's fairly, there's no interference because it's sort of all on one side. Maybe that's not right, but I bet there's a direct analog.
Well, yeah, I mean, it's kind of saying if orange is going to win on, the left side of the board, I don't really care what purple does on the right side of the board, right? That contributes nothing to my amplitudes.
Yeah, but how does that affect? How does that give you? Where do we see the interference pattern on the board, so to speak?
Right. Well, yeah, I mean that depends on the details of how you do this projection.
Well, but I think that's the name of the story. I mean, because we're saying there is a unique phase that determines our distance in Scorespace. But this is the nub of the double slit experiment, is this question of the fact that Scorespace is some kind of space-filling curve mapping relative to physical space. So in this case, right, Scorespace, we have to ask the question, how does Scorespace map onto board space?
In this case, it's whoever has the most threats.
Yeah, but the question, Ed, is when we're looking at the physical space of the board, wow, how does this work? Given two board positions, we can say, what is their score difference? What is their relative score?
Well, but the underlying point is you can also say for each place for each location on the board where I could place an X or an O, what is the marginal change in score?
Sure.
And that's effectively giving you a phase coordinatization of the board at any point in time.
Right. Okay. So you're saying, given a particular board position, if I am going to place another mark, how are my possible moves, rated in score/phase? I'm telling you that this whole business about the question of the mapping of this messy Hilbert spacey thing like this into finite dimensional, positions of fringes and things, that's clearly a big part of the story. And that's where, for example, in this whole discussion about branchial space coordination, it's like, how does that work? Right? In other words, there are certain natural coordinations that you could imagine. I mean, my guess is the answer will be that this story of what the coordination is a story of what the observer can reasonably create. That is, it'll be a story not dissimilar to the story of statistical mechanics, the story of the second law and things like that, that is asking, what is the reasonable way that that an observer would coordinatize this messy space? Just like in general relativity, an observer could coordinatize space-time in some totally wacky way, which would conclude that there's, black holes at every street corner. Right? But one doesn't do that because it inevitably would lead to all kinds of weird things that would be hard to even compute what the coordinate system looks like.
Oh yeah, exactly. I mean, it's the standard story we've seen a whole bunch of times now. It's just the relationship between reference frames and computational complexity.
Right, but so the question here is, again, what has to be argued is that the double slit experiment and all these other things are doing their coordination of branchial space according to certain principles that are essentially a simplicity of reference frames principles. Just like, okay, here's my argument. So special relativity is a story of simplicity of reference frames. If you don't have the idea of an inertial frame, you don't get special relativity. You get, in other words, if you don't think about that kind of simple way of setting up a frame, you don't get the effects of special relativity. So similarly, the claim would be that the double slit experiment, in a sense, you are thinking about a simple quantum observation frame, and that's why you get the sort of simple to interpret result that corresponds to that, and that is some kind of way of coordinatizing this complicated branchial space, which in the case of your analysis of the double slit thing corresponds to some kind of space-filling curve going through, the situation you have there is this two-dimensional space defined by the two photons, basically, which you are then coordinatizing by making a space-filling curve around it.
Exactly.
Right, but the argument that it is a space-filling curve requires essentially an axiomatization of what is a reasonable reference frame.
Well, it depends upon this correspondence between reference frames and computational boundedness.
Well, I understand, but so that,
because the algorithmic complexity of a space filling of the Hilbert space filling curve is basically minimal, that's like the analog of an inertial frame.
Well, I understand, but the statement that the statement of what type of thing, so an inertial frame, ever since Galileo, basically, we have the kind of the rough idea of an inertial frame. Right? It's an unsurprising, but in the case of quantum mechanics, let's put a Hilbert curve in branchial space is hardly the most obvious, been around for 300 years type story.
Right.
So the question is, what is our criterion? Just like an inertial frame is, a Newton's first law story or whatever. What is the analogous story for the type of quantum observation frame that we will choose to use?
Right. So like I said, I've primarily been using essentially an algorithmic complexity measure. Right. The harder it is to specify the frame, the less natural it is.
Yes, but it would be nice to axiomatize that in a more convincing way, because
Sure.
that statement, your statement is, in the quantum case, as in the statistical mechanics or whatever, we are thrown immediately into the, right. I'm sure this is basically correct. It would just be nice to see. Yeah, all right, okay. Well, you've got to go to our different things here, but all kinds of comments on our live stream about boy. I'm just looking down, all sorts of fascinating things. Interesting work in quantum finance and the quantum stock market. I wonder whether that relates to some other things that we are looking at. Quantum Nash equilibria. Oh, I don't understand any of that.
Well, actually, we shouldn't discuss it now, but the thing that you and Ed were talking about right at the beginning, or that Ed was discussing about, if you have situations where you have two players and they can place a piece in the same region of the board, and then Ed mentioned, you said that there are like 3 canonical ways of resolving that, right?
Yes. I won't repeat them now.
Okay, yeah, but they would like, one player misses a turn, or, one player gets it, or they both move there, or neither of them move there.
Yeah,
So,
and that's analogous to double spend. Yes,
exactly.
I get it. That's very interesting. Yes.
And then it can be complicated with sandpile models.
All right, we need to understand that's a conflict resolution. Those are different ways of resolving. It's just like in the case of locks in parallel computation. Yes, very interesting. Okay, what on earth is this? I have to look at one thing that came on our live stream because there are always interesting things here. What is constructive geometry? Constructive gravity, rather. What on earth is this? I don't know what this is. Well, it looks interesting. Okay, something possibly for our collection of related things. Okay, I gotta go. Thanks, everyone. Thanks, Jonathan. You sounded a bit impatient here. I know you want to work on ZX calculus and so on.
I'm convinced that, ZX calculus is, at least for me, helping me understand phase a lot better.
Okay, when are you going to explain that to me? I think I understood from your previous description of ZX calculus. I think I'm not totally clueless now about how that works, and
sure.
and that has a way of representing phase in terms of z's and x's and so on, presumably by combinations of those.
Well, exactly. So each z and x spider has a phase associated with it in the definition of the calculus anyway. And so it's like it's really nice because, in a sense, we know what the answer should be. And so then we can just check what coordinatizations of branchial space give us the right answer. And surprise, surprise, for the 1-dimensional and 2-dimensional cases I've tried so far, they turn out to be space-filling curves, which is quite exciting.
Oh, that's wonderful. Really?
Yes.
How on earth does that work? I'm
still trying to get to the bottom of it, but it's
But how does that work? How does it even know to make a thing like a space-filling curve? It's just how weird.
I think I should talk to Matthew about this, because basically what I've managed to get to is the point where, so what's happening is when you write one of these ZX expressions out, not in the graph form, but in the operator form, when you take the branchial graph and you project it onto a particular diagram, what you're basically doing is you're defining a pairing function across all of the different arguments of each operator. And because of this correspondence between pairing functions and space-filling curves, you somehow get a space-filling curve.
You know what I bet it is? I bet in an operator representation that this corresponds to some kind of depth first traverse through some operator tree, and that corresponds when you unravel that's going to correspond to this Hilbert curve or something.
That's probably it. But I think Matthew, being the resident,
is the world expert in pairing functions.
Exactly. I think you should
right, you should. Yes. Fascinating. Well, that's wonderful. Well, okay, many things are converging. This is really good. Great. All right, I got to go. See you all. Thanks to folks on the live stream. Lots of interesting comments as usual, and lots of things we didn't have a chance to respond to. Sorry.